Hi there, another video. This is the electricity multiple choice booklet, so feel free to pause the video at the questions and then attempt the questions yourself. Resume playing, and as always I will explain how to do the questions. First of all, question 1. The overhead cables used to transmit electrical power by the national grid usually consist of a central core of steel cables surrounded by a sheath of cables of low resistivity material, such as aluminium. What is the main purpose of the steel core? The low resistivity cables on the outside are for transmitting the electric current. The core of steel cables is simply to increase the mechanical strength of the cables. Here's a question. Number 2. Two resistors, R1 and R2, are made of wires of the same material. The wire used for R1 has half the diameter and is twice as long as the wire used for R2. So what we need to know here is the relationship between resistance and cross-sectional area and the relationship between resistance and length. So if you ever forget these, you can simply use the resistivity equation. So resistance is equal to resistivity times length divided by area. And that will give you the relationship. So the first relationship is that resistance is directly proportional to the length, and resistance is inversely proportional to cross-sectional area. And these two are the relationships which we will use now. Just going to remove all this and make some room. In fact, I'll pop these at the side. So resistance is proportional to length, inversely proportional to cross-sectional area. So let's deal with the length first. It's twice as long. So resistor 1, if it's twice as long, we'll have double the length, which will double the resistance. So I've got a times 2R just to begin with. Then we can look at the cross-sectional area. It has half the diameter. So if you half the diameter, you're also obviously halving the radius, and cross-sectional area is equal to pi r squared. So if we half the radius, a half squared is a quarter. We end up with a quarter of the cross-sectional area. Going back to our relationship between resistance and cross-sectional area, if we get a quarter of the area, that means that the resistance would go up and do the opposite because they're inversely proportional. The resistance would go up by a factor of 4. So we get a times 4R. So essentially we've now got a times 4 and a times 2. So the resistance of R1 would be 2 times 4, so 8 times greater. So the ratio R1 over R2 would be 8 lots of resistance divided by 1 lot of resistance. They cancel out, leaves us with 8, so the answer is A. Right, let's move on. Attempt this one if you wish. A 1 kilo ohm resistor is thermally insulated and a potential difference of 6 volts is applied to it for 2 minutes. The thermal capacity of the resistor is 9 joules per Kelvin. So what that means is that if you give it 9 joules of energy, its temperature will increase by 1 Kelvin. So the rise in temperature in Kelvin gives you the 4 options, and we'll figure this one out now. So what we need to do in this question is calculate the power. So the power is equal to V squared divided by R. So power is equal to V squared, 6 squared is 36, divided by 1000. This is 0.036 watts. Then we can calculate the total amount of energy. Energy is simply power times time. So the power is 0.036, so 0.036 multiplied by the time of 2 minutes, which we need to convert into seconds, which is 120 seconds. And 0.036 multiplied by 120 is 4.32 joules. And then what we need to do is we need to do 4.32 joules divided by 9 joules per Kelvin. So what you'll see is that the joules will cancel, Kelvin goes to the top, and the 4.32 divided by 9 gives us the answer C, 0.48, and the unit would be Kelvin. So 0.48 Kelvin. So the answer is C. And to remove that, let's go to the next one. Question 4. A metal wire is maintained at a constant temperature. Which one of the following graphs best represents the relationship between the dissipated power P and the current I in the wire? Simply, power is equal to I squared R. R is constant. So power is proportional to I squared, which is the old Y equals X squared type graph. So the answer must be C. Let's move on to the next one, number 5. These can be quite tricky. What you have to do with these questions is to redraw them. So the diagram shows a network of 4 2-ohm resistors, as given, and it says the effective resistance in ohms between X and Y is. So essentially what we do is we have X as a starting point and Y as the finish point. So what I'll do on the right hand side here is redraw this circuit in a manner that's more familiar. So what I'm going to do first of all is to put X at the top and Y at the bottom. And then we'll just fill in between. So let's start at X here. One of the paths, so initially we have a junction, and one of the paths goes through the 2-ohm resistor straight to the finish point X. So I'm going to go this side. I'll try and keep this as neat as I can. So a 2-ohm resistor, I'll just write a 2 inside, and then straight to Y, So that's that side done, that's finished. Then what happens is we can go another direction, where we go straight through a 2-ohm resistor to a junction. So on this side, I'm going to go through a 2-ohm resistor and get to a junction. Then at this junction, we split into 2 and we go through a 2-ohm resistor directly to Y. And the other direction goes through a 2-ohm resistor also directly to Y. So these two, this one and this one, are definitely in parallel with each other, like this. So 2-ohm resistor one way, and a 2-ohm resistor the other direction. They'll join back together, and both join to meet at Y. So now if you wish to pause and attempt this, that's fine. This is in a much more familiar format, and I'll show you how to complete that now. So these two resistors are in parallel, so I'll deal with these first. So parallel combination, 1 over RT is equal to 1 over 2 plus 1 over 2. So a half plus a half is 1. And then obviously 1 over 1, because you have to flip to get RT, is just simply 1. So I'll just write that for the combination. The combination is 1 ohm. Then we can deal with the rest of this side. So we've got the combination is 1. And then in series above that, the total combination on this side is 1 plus 2. So we've got 3 ohms on this side. So I'll just write 3 ohms. On the opposing side, we have 2 ohms. Then it's very simply a simple circuit with a 3 ohm resistor on one side and a 2 ohm resistor on the other. And we just need to find out the equivalent resistance. So 1 over RT in parallel is 1 over 3 plus 1 over 2, which is equal to, so that's over 6 and then 5. Then to get the resistance, we just need to do the inverse. So when it was 6 over 5, so the answer is 6 over 5, which gives us 1.2 ohms. If you've just done that question for the first time, I may advise that you would just rewind and do that question again, as it is quite a tricky one. Let's move on. Question 6. To zoom this out for a moment. So the diagram shows 2 wires, P and Q, of equal length, joined in series with a cell. A voltmeter is connected between the end of Q and the point X on the wires. So this is the point Q and some point X. The potential difference across the cell is V. A wire Q has twice the area of cross-section and twice the resistivity of wire P. The variation of the voltmeter reading as the point X is moved across the wires is best shown by. So if you want to look at these graphs, you have to pick which combination shows how the voltage varies with the distance. I'll look at that one now. So what we first need to establish is any differences between the X part of the wire and the Q part of the wire. So the X part of the wire, we can say has resistance R, so the X part of the wire has resistance R. And we need to look at the Q. So resistance is equal to resistivity times length divided by cross-sectional area. And the difference between the wires is it has double the resistivity, yet it has double the cross-sectional area. So the twos will obviously cancel. So the resistance of X and Q is actually equivalent, it's the same. So that's the first thing. So as the voltmeter is at full, the voltage across the entire thing would obviously be equal to the supply voltage. So the voltage would start off high and then decrease in a linear fashion as the resistance of the wire XQ is consistent. So we just end up with a straight line. So the answer would simply be B. Let's move on to the next one. So question 7. Copper metal is a good conductor of electricity because copper atoms in a copper metal, well, they're actually copper ions inside the wires. So the reason they're ions is because they've lost an electron. So we have positive ions. And we have a bunch of free electrons which are free to move about throughout the conductor, making them a better conductor. So the answer is simply D. Let's move on to question 8. So the 12-volt battery in the circuit shown as negligible internal resistance. The diodes have ideal characteristics. If you'd like to have a go at this, please do. So this may seem complicated on the surface, but it's actually not. So the ideal characteristics would insinuate that the current, obviously we need to know, goes from positive to negative. So the current is actually going to go this way. So as the current goes this way, this diode is in the correct orientation to allow current through. So the current will flow through this part of the circuit. Fine. However, on this side of the circuit, the diode is in the reverse orientation or reverse bias, which means that no current can actually flow this way. So essentially this part of the circuit doesn't exist. So we're just dealing with the top bit. So the current it's approximately, so current would equal total voltage divided by total resistance. So the total voltage is 12, total resistance is 60. So the current for the battery is approximately 0.2 amps or 0.20 amps. So the answer to this one, to number 8, is C. So have a look at this one, number 9. If you want to have a go at that, please do. A 1.5 metre length of wire has a cross-sectional area of 5 times 10 to the minus 8 square metres. When a potential difference across its ends is 0.2 volts, it carries a current of 0.4 amps. The resistivity of the material from which the wire is made is... So this is pretty simple. So resistivity is equal to resistance times cross-sectional area divided by length. So the resistance we can get from voltage divided by current. So 0.2 divided by 0.4, which is a half. So the resistivity is 0.5 times the cross-sectional area, which is 5 times 10 to the power minus 8, divided by the length, 1.5. Put that in your calculator and you will get approximately 1.7 times 10 to the minus 8 ohm meters.